Welcome to the electronics class for November the 19th. Okay, guys, so I have looked over the binary adder, or well, actually the binary number assignment that was due last week. And it looks like everybody got a really good score on that. Almost everybody got a really good score on that. So congratulations. It sounds like you guys, or it seems like you guys understand binary numbers really well. So there was nothing officially due today. The midterm exam, the binary adder, that's due next time we meet. But 4 of you have submitted the binary adder. And so 3 of you got it perfectly right. And 1 of you got it really, really close. I mean, it added everything right, but you didn't put resistors in your LEDs. On the input LEDs you did, but on your output LEDs you didn't put resistors. And under some circumstances, what happened was you were getting a little too much current flowing through your resistors. So you know that little exclamation mark that you see sometimes? So you were getting that sometimes. Now, other times you weren't. It depended on how many LEDs were turned on at the same time. But there were some instances where you did get that little exclamation mark because you were letting too much current flow through your resistor, through your LED. So I dinged you a point for that, but only 1 point. I mean, you still got 99 out of 100, so it's still an A+. But still, finger wag. I mean, somebody at this stage of the game here in electronics, you should know how to protect your LEDs with resistors so you don't let too much current flow through them. Okay, so I did get a couple of people telling me that they're having trouble because the binary adder, you know, there's so many wires, and yeah, it's easy to get them mixed up. So last time I gave you a suggestion for how to deal with that. So I'm going to talk about that a little bit today. But before I do that, let me show you something that you may have seen when you logged into Aspire just now, or I'm sorry, when you logged into Canvas just now. And you went, if you looked at the assignments, you will have noticed that I've added in something new here. Let me make this be a little bit bigger here. And let me hide this here. Okay. So, let me get out my pen here. Okay. So this is the original midterm exam, build a binary adder circuit. So we talked about that. That's due next time we meet. It's worth 100 points. Now, if you are having trouble getting this right, you know, you sat there and you spent all sorts of time trying to get this darn thing right, and it's just not working for you. I have added another alternate midterm exam up here that you can take. If you don't want to do this one, you can do this one. This is an easier one, but because it's easier, the best you can hope for if you do this one is to get a C. So I don't recommend that you do this one. I recommend you stick with the original one, but if all else fails, you can do this easier binary adder circuit. Hey, a C is better than an F. Now, those of you who have already completed the binary adder circuit, or those of you that do complete it in the next day or so, if you would like a little bit of extra credit, I will give you extra credit for doing this alternate thing here. So let's talk about the alternate thing first, and then we'll come back and then we'll talk about the real one. Okay, so if you click on this alternate assignment now, what you will see is that there is a chip on Tinkercad that I know at least one of you was already aware of, because when I initially signed this binary circuit, you remember that one of you said, well, hey, why don't you just use the 4-bit binary adder? Because there is a chip that it was designed to do binary addition. And the chip is the one that you see on here right now. okay? And the pin map for the chip is shown right here. This one chip can do everything that you need to do. So let me just show you how this works. And so it's definitely much easier here, right? So before I do that, so this is the circuit that I was hoping that you would all make, and you can see there's a big spaghetti of wires there. Now, I've routed them the way that I have in order to make it easy to see what goes where. I noticed that when those of you that submitted your circuit to me previously, you didn't route them quite as nice. And so I can understand why you may have had a lot of trouble figuring out where your problems are if it doesn't work right. So I strongly recommend that you route your wires like this, but hey, I don't require it. Okay, so let's take a look at that easier binary adder circuit. Okay, so, okay, so right here, this one here, this is the binary adder circuit that does everything in one chip. There's this integrated circuit that was specifically designed simply for the purpose of adding binary numbers. And if you were to look inside this chip, you'll find there's a whole bunch of AND gates and OR gates and NOT gates, okay? And so this one chip can do the job that all of those other messy ones did. And you see, this is really easy. As long as you know which pins go where. And so if you look right here, this is the thing that tells you which pins go where. So remember the way that these things work. This guy here is pin number 1, 2, 3, 4, 5, 6, 7, 8, 9, dot, 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 all the way up to 16. Okay, so the input numbers for your first digit go in pins 5, 3, 14, and 12. Okay, so, and by the way, you notice this is a 4-bit adder, not just a 2-bit. So let's, first off, let's talk and let's find out what does it mean about 4-bit and 2-bit and all that kind of stuff. So if you come back to this thing that this is the one that we were working on here. So we had this binary number added to this binary number. So you can see that each one of these binary numbers can only have 2 digits. So we can have like 0, 0, we can have 1, 1, we can have 1, 0, okay? So this is what we call a 2-bit number over here being added to a 2-bit number, and you'll see that our output, our answer, is a 3-bit number. But these guys over here, these are just 2 bits. So the biggest number that you can represent, the biggest decimal number that you can represent if you're restricted only 2 bits would be the number 1, 1, which corresponds, so that would be a 2 and that would be 1. So the number 3. So if we only use 2 bits, the biggest number that we could possibly add would be 3 plus 3, okay? And so that's it. If we could allow ourselves some more bits, then we could add bigger numbers. And so this circuit that you see right here, okay, this is a 4-bit adder. So it could actually add, so the biggest number that you could add with this guy would be the binary number 1, 1, 1, 1. So that would be 1 plus 2 plus 4 plus 8. So that'd be 12, 14, 15. So you could do 15 plus 15 if you use 4 bits. So your input here, you have 4 bits. Now in the example that I'm showing you right here, I've kept it down to 2 bits, okay? But you can see with this one chip right here, okay, this one chip here, it can do the job. And if you don't believe me, let's see, okay? Let's fire this baby up and see if it works right. So I'm going to start my simulation. And so right now I've got 0 plus 0 equals 0. So if I make it a 1, okay, so I've got 1 plus 0, okay, it equals 1. Okay, so how about let's do 1 plus 1. Hey, you can see it equals 2. Okay, how about let's do 1 plus 3? Yep, you can see it's 4. So what about 3 plus 3? Hey, yep, you can see it's 6. So this thing does do the job, and it does it really, really easy. So if you cannot get the other binary adder to work, the one that uses the AND gates and the OR gates and the NOT gates, I will let you use this right here. But the best that I can give you then is a C if you do that. Okay. Now, I just got through saying that this chip can actually add 4-bit numbers. So let's go in here. Let's take a look at this. So here I've got that same chip, but this time I've made my input numbers be 4-bit numbers. So let's take a look at it. If Tinkercad will, okay, there we go. Okay. All right. So what you can see here is now I've got a 4-bit number added to another 4-bit number. And you can see my output is a 5-bit number because it makes sense. Your output has to be bigger than your input. All right, so let's start up the simulation and let's add a couple numbers. So let's try 1 plus 1. So there's 1. Actually, let's try 1 plus 0. Okay, so 1 plus 0 is 1. All right, 1 plus 1 is 2, so forth and so on. Okay, how about this one? Okay, so what I'm going to do is I'm going to put a number here, and okay, how about that one? So I want everybody to practice your binary skills. I want you to tell me what is the decimal number that is equivalent to this, and then so you're going to give me some number here that's going to be decimal. And then I want you to tell me what is the decimal number that's equivalent to that. And then I want you to tell me what is the decimal number that's equivalent to that. And let's see if this binary adder is working. Okay, so I want you to put it into the chat box in a private message. I don't want everybody else to see your answer. Okay, so what is the equation? So type it in as some number plus some other number equals a third number. All right, good. I'm seeing two people have given me full equations. Let's get a couple more here. Okay, good. Okay, Dallas, try that one again. Okay, Presley, your first one is wrong. The second one is right. Okay, good. It looks like pretty much everybody is agreeing. Okay, well, everybody's getting it now. Okay, so what we have here is this guy is the equivalent of 9. This guy here is the equivalent of 5. And when we add them together, we get this, which is the equivalent of 14. And so 9 plus 5 does in fact equal 14. So good. Okay, so this is available for you to do as an alternate assignment if you cannot get the real one working. Now, those of you that can get the real one working, if you're looking for a little extra credit, hey, tell you what, I'll give you some extra credit. If you do this alternate adder here using this chip, the 74HC283 chip, okay, I'll give you a little extra credit. Now, I'm not going to give you a lot of extra credit because it's pretty easy, but yeah, I'll give you a little extra credit. I think it's a good experience for you to do this. Okay. Now, there is one other thing that we can do. I mean, if you really want to take this to extremes, if you really want to go super cool here, there is another chip in the Tinkercad collection of chips. And it's a chip that can automatically convert from binary to digital. And if you hook it up together with a special thing called a 7-segment display, then it'll work. So here is my binary adder with a 7-segment display in it. If Tinkercad will come around. I really wish they would find some way to speed up Tinkercad here. Wow, It's really slow this time. Tell you what, while we're waiting for Tinkercad to come on, let me come back here. All right. So those of you that are having trouble, let me retell you something that I told you last time, but I think it's worth saying again. There is a technique that will make this a lot easier for you to do. So let's click in here and then let's come down. Okay. So I told you this last time, but I'm going to tell it again because it really will help a lot. What I recommend is that you guys take each one of these chips and give it a name. Call this one the A1 gate and call this one the A2 gate. And this is the A3 and this is the A4 and down here over here this is the A5 and this is the A6. All right. And then do the same thing for the OR gate. So let's call this O1, call this O2, call this one O3, call this one O4. And then for the NOT gates, all right, so then we can call this N1, call this guy N2, call this guy N3. All right, so then if you have these labeled, then you can say that let's look at our OR gate right here. You can see that the output from the O1 OR gate goes to the input of the A4 AND gate. Okay, and that's all it goes. But if you look at this one, so the output from the A1 AND gate, it goes to the input of the N1 NOT gate, and it also goes to the input of the O4. If you label these, then when you have your integrated chip, okay, you can see that these three chips right here, label that as your A1, or these three leads, label that as your A1 gate. And let's see, it looks like I need one more there. Okay, so these guys, these are your A2 gate. And then these guys here would be your A3 gate. These guys here would be your A4. So if you label them, then it will make it so that what previously seemed like a totally unorganized, undoable problem, all of a sudden becomes doable. So I highly recommend you do that. And I think that if you do that, you'll find that this problem is not that bad. Okay, let's go back to Tinkercad and see if it, okay, good, it came up. All right, now, if you guys are interested, now this is not a required assignment. This is just something that you could do if you want. These chips that you see right here, the CD4511 chip, that is a chip that has been specially designed so that it can decode from binary to decimal. And if you hook it up together with this special thing here that's called a 7-segment LED display, okay? So the way it works is that, oh boy, I hate it when sometimes the mouse clicker gets stuck. Okay, so if I hover over this pin, you can see that it says F, and this one is common, so that means it's ground. But I've also got a common down here, so it's you don't need both of these connected to the ground. You only need one of them connected to ground. Okay, so this pin here is B, this pin here is A. So each one of these segments, so like this segment, oh, let's see, that doesn't show up very well. Let me try yellow. Okay, so this segment corresponds to one of the letters. It's either A, B, C, or D. And this segment is a different one, and this segment is a different one, and this segment is each one of these segments has got a code number. And so, like, for instance, this segment here is the A segment. And if you hover over these, it tells you which pin gets connected to which segment. So there's my A segment, okay? So if I connect up the A wire here, okay, you see I've got it connected up. So that goes to the A segment. So it comes from the A output of my CD4511 chip. and it goes into the A input on my 7-segment display. Okay, so that's the output there, and make sure that you put a resistor in here. I recommend to use a 1 kilo ohm resistor, because if you don't, then you're gonna have too much current. You're gonna destroy it. Okay, and then these pins down here, these are your inputs. So you can see this is input 2, input 3, and this is just a lamp test. You just make this one be always high. Just have 5 volts go into this one. And the one that says blanking, just make that one always be high too. Okay, and then the latch enable, make that one always be low. Okay, and then here's input 4, and then here's input 1. Okay, so those are the inputs. So if I zoom out a bit here, not in, I want out. Okay, so you can see how I've done this. So this pin right here, okay, so this is my A1 digit. This is my A2 digit. So when I click this button, when I click that button, okay, so in addition to sending the electricity, or let me make that be black so it shows up a little better. Okay, so when I push that button, it sends the electricity over here into my binary adder, but it also sends a signal down here to my binary decoder. And then the same thing with this other one, it goes into here. Okay, so let's see how this works. Let me clear this out here and let me show you. So I'm going to start my simulation. So right now I've got nothing here, nothing here. So you can see down below on my binary decoder, you can see I've got a 0 plus 0 equals 0. And you can see that corresponds to up here. Okay, so what if I want to do 1 plus 0? All right, so let's set this for 1. Okay, so you can see I've got a binary 1 plus a binary 0. But if you look down at the bottom here, you can see that my decoder is recognizing that I've got a number 1 plus 0 equals 0. Okay, so let's try a couple more. Let's try doing about 3 plus 1. Okay, so if you look on my decoder down here, you can see I've got 3, which corresponds to that. And then you can see I've got 1, which corresponds to that. And then finally, you can see I've got 4, which corresponds to that. Okay, so if you guys were to make a circuit that looks like this, then I'll give you lots of extra credit. Okay, you don't have to do this if you want. You can leave this out. If all you do is this up here, I'll give you a little bit of extra credit. But if you do the whole thing, then I will give you a lot of extra credit. Okay. So are there any questions from you guys about this? Not seeing any questions, not hearing any questions. Okay, so Caden said,
what's the max grade you could get if you just do this here, not the other assignment for it?
Okay.
With
All right.
the sentence displays with it.
Okay, that's an important question. Thank you for asking that. Okay, so if, let's see, let me get my annotation here so I can do some drawing. Okay, if all you do is this circuit up here and you don't do this circuit down here, the best that I would give you is a C. If on the other hand, if you do both of them, if you do the entire thing, but you don't do the original test, but you do both of these, I would give you an A. I think you deserve an A because as you can see down here, this is kind of complicated. So yeah, if you do both of these together and you don't do the other one, I will give you an A. Okay. if you do all of them, then what I'll do is I'll give you extra credit, and I'll give you quite a bit of extra credit. Okay. Any other questions? Okay, so now remember, guys, the assignment. Let's see. Let's go back to here. Okay, so the due date for these guys. Let's go. Here we go. Okay, so the due date for the original test is next time we meet, November 21st. The due date for this alternate assignment is the next Saturday, the 24th. Or actually, is that? That was what I intended, but now I'm beginning to wonder, did I mess up? Let me open up a calendar really quick and see. What day is the 24th?
It's the 19th today.
Yeah, today's the 19th, but what day is, the 24th is the next time we meet. So the 24th is next Tuesday. Okay, so you've got until next Tuesday to do the alternate assignment. But remember that this alternate assignment is optional. You don't have to do it if you don't want, but I think it's fun, and it certainly will give you some points. So, hey, worth doing. Okay, well, that's all I have for you today. It's so good grief. We've got over a half an hour. We've got 40 minutes left in the period. So what I would recommend is use the remaining time to get working on the midterm exam. I highly recommend that you do the original midterm exam. I think it's a very good experience. Actually, tell you what, before you guys log off, let me just show you one more thing that I think is worth you seeing. Okay, I just want to just remind you how much you have learned, because you may not realize how much you've learned. So we started off learning how to take transistors and resistors and make logic gates. Okay, then we actually made some logic gates, okay, using what we call discrete transistors. Remember that word, discrete. Okay, so each transistor that we used was in its own package. Each resistor that we used was in its own package. Okay, then we learned that it's possible to combine these guys schematically, at least, into these and not and or symbols. And then we learned that there's these really neat things called integrated circuits. So each one of the 4 chips that you see right here has a whole bunch of resistors and transistors all packaged inside, where they're all integrated together inside that one package. So that, I mean, if you think this is complicated right here, imagine how much worse it would be if you tried to do a binary adder using discrete resistors and transistors. Holy cow, would that ever be a mess? Okay, so by using these integrated circuits here, it makes it a whole lot easier. But we can take the integration level one higher. This new chip that we learned about today, this one that's called the binary adder, this one chip has a whole bunch of AND and OR gates built into it. All of the AND and OR gates that you see here, plus a few extra, those are all jammed into this one chip. So the level of integration is getting higher. We've got, there could easily be 100 or more transistors and resistors all packed inside this one chip here. So, but what we're doing is we're going to higher and higher levels of integration. Okay, so if you were to look at the Arduino, so this chip that you see on the Arduino, this thing has literally got millions of transistors and resistors inside of it, literally millions.
Don't make us make one of those.
Yeah, these are really complicated to make these. You have to shrink the transistor and the resistors down to super, super small numbers. And by the way, Guess what I used to do for a living before I became a teacher? I made these. Okay. They I'm one of the people that put the micro in microchip here. I invented the equipment that's used to make these things and to make them smaller and smaller and smaller. So there are chips that you can buy today that have billions with a B. There are literally actually tens of billions of transistors and tens of billions of resistors all jammed into one tiny little chip. Okay. So the amount of technology that goes into these is phenomenal. And it was a blast. I loved doing that job. It was a lot of fun and it pays really well too. So if you guys are looking for a job, by the way, these are called semiconductor chips. So the semiconductor industry is a great industry to work in. And I think you guys are gaining exactly the kind of skills that you need, that you could get a good job in the semiconductor industry. Okay, well, that's pretty much it. So if you don't have any questions, then you can go ahead and type "buy" into the chat box and get working either on the original binary adder or the new version of it. If you do have a question, I'll stick around so you can ask your question. And I'll even turn off the recording so you can ask the question without the embarrassment of knowing that it's being recorded.